Now, there are other types of isomers apart from structural ones. Structural ones you would have encountered in Year 12, and they can have different functional groups. They just have to have the same molecular formula. They will have a different name because they are a different structure. Now, stereoisomers are isomers that, to all intents and purposes, appear to be the same, but because of a different arrangement of the groups around an atom, they are actually different. So these would actually have the same name, and we have to come up with a way of naming them a little bit differently. Now, geometrical isomers, remember, have the cis-trans, where you have the double bond, and you have the double bond preventing rotation. So if for instance, these two methyl groups are down below, they would be considered cis, but if we were to shift that one up, it would become a trans isomer, and so the geometry is altered based on the fact that the double bond prevents rotation, and therefore these groups can't move. Normally, if you have a single bond, the atoms are free to move around in space around that bond, a bit like a bicycle wheel spinning in a way, but that's geometrical isomers, and you should have seen those in Year 12. Now, geometrical isomers are a type of stereoisomer where you just have this, the image is different, but it does have the same name. Optical isomers are what we see in Year 13, and this is based on the fact that these two isomers, there's going to be a left and a right, or a levo and a dextro, just the same word, left and right. And if you pass plain polarized light through a sample, now this is just an animation showing how normal light moves in all directions as it moves away from a light source. Now, we can apply a filter to this, and what that makes it is that the light is polarized so that it only travels in a single plane. So, and we then place it so that it passes through a sample. Now, as it moves through this sample, the light may be rotated as it passed through, and it's rotated a certain number of degrees. It may be anti-clockwise or clockwise or left or right. There's often different ways of describing it. Now, if we take the optical isomer of this, B, we'll find it rotates it by the same number of degrees in the opposite direction. And this is why they're called optical isomers, because of their ability to rotate plane polarized light. Okay. Anyway, now another name for an optical isomer is an enantiomer, so you should know that as well. Now, optical isomers have 4 different groups attached to them, and one thing you should have done in class is seen that they cannot be superimposed on each other. What does this mean? Well, what it means is in a similar way to your left and right hand. They look pretty much exactly the same, and they look like mirror images, but if you were to place your hand flat down on a table and try and place the other hand on top of it, you'd find that your thumb overlaps with the little finger and that you can't do it. So that's the inability to be superimposed. And if you have access to a Molly-Mod kit, your teacher should have shown you how this works. Okay. Now, how do you spot a optical isomer? Well, all you've got to do is find what we call the asymmetrical carbon, and it has 4 different groups attached to it. Now, this has been drawn out in a 3D way, so it's easy to see. But let's look at some other examples. Okay, now, if we were to look at these 4 molecules and we're asked which one of these is capable of having an optical isomer or exhibiting optical activity, we just have to find a carbon which has got 4 different groups around it. Now, if we look at this carbon here, for this one, it's got an OH group, an H, and another H, and as soon as we do a second H, obviously they're the same, so it stops there. And if we look at these carbons, they all have two H's or multiple H's, so this one doesn't work. Now, one thing also is if you ever see a carbon with a double bond, immediately that means this carbon cannot be what we call the asymmetrical carbon or the chiral carbon, because it can't have four different groups if two bonds are used. Now if we look at this one, the bottom one, okay, this carbon here has got three H's, this carbon here has got two H's, this carbon here has got this group, this group, this group, and this group. Notice we aren't just looking at the adjacent carbon, we're looking at everything that is part of the adjacent group. So this would appear initially to have four different groups, but if we look at this one and this one, they're both methyl groups. So this one doesn't have optical activity. If we look at this one, the first carbon obviously has multiple H's. The second one though has an OH, this methyl group here, an H, and then this ethyl group here. So that does have four different groups. Now it is possible to have within a molecule more than one chiral carbon. And for instance, if I was asked to mark it, I would mark this one. This particular molecule, butanol, only has one chiral carbon, which I've just marked. Now if you're asked to draw a 3D representation of it, I always start with a basic outline, which is kind of my template for doing 3D structures. These straight lines I'm drawing are supposed to be in the plane of the page. This bulky line I'm now drawing is supposed to represent it coming out the page towards you, whereas this one going back, which I'm trying to draw, which isn't shaded in, is supposed to mean it's going back. This is supposed to be a tetrahedral shape that I'm drawing right now. And this is what you drew for any of them. And I'm just repeating it over here, because if we are asked to do a 3D drawing of one, or indeed if we're asked just to draw the two isomers, this is what we need to do. Now, all I have to do is now put these four different groups that I've circled here around each part of these little sticks that I've just done coming out. So for instance, I'll put the OH here, and it doesn't really matter, you know, where I put them, as long as I put them in a logical way. I'm going to try and show them in terms of how they bond. Now on the second one here, all that matters is that I swap any two groups. So if I swap this and this, that's fine. It can be any two though. Alright, so I'll put an H there, and I'll put the OH there. Oops, I haven't swapped those right, have I? So just a minute. I'll put the OH here rather, and the H there, so I'm just making sure I've swapped them correctly. And we're going to leave the CH2, CH3 here, and we're going to leave the CH3 here. So having done that, I now have drawn the two optical isomers for this. Okay, you do not need to know which one rotates light either left to right or clockwise or anti-clockwise, because you'll only find that out if you did that as a physical test in the lab with plain polarized light. Now sometimes students get confused over two particular questions. One, how did you identify it? So how did you identify it? What they're asking you to talk about is how they have four different groups attached. And you don't use the word atoms, because remember, these can be fairly large groups. Four different groups attached to the chiral carbon. You could also say asymmetrical carbon. That's how you actually identified it, that's how you spotted it. Now, how can you do a physical test for it? Or how do you test for it? Either way, you're going to be talking about how, if you pass plain polarized light, which is PPL, so if you pass it through each sample, they will rotate it in opposite directions. Okay, so that's a physical test. It's important to remember that. What are some of the similarities that they have? Well, they have the same physical properties. I mean, these molecules are pretty much exactly the same. So when we talk about physical properties, it's important you identify what they are. They're things like melting point, boiling point, density, that's the number of particles in a given volume, same solubility, okay, and they also have the same chemical reactions. So, you know, if it's an alcohol, they're both going to be oxidized. So, you know, and if you know, it could be oxidation, it could be an acid-base reaction, so that depends a little bit on the actual chemical that you've identified. And, you know, they may react with those the same, it just depends. Okay. What else is the same about them? Well, actually that's a considerable amount just in itself. The differences are a little bit harder to establish, but if we look at the differences, obviously there's the plain polarized light you could mention that gets rotated in different directions. Now I'm just kind of simplifying this down to almost bullet points. You wouldn't do that in exam. And also they cannot be superimposed. And there's one more significant point which is very important, and that is biological activity. Now, even though the chemical reactions tend to be the same, in many systems, by systems I'm talking biological systems, we have either enzymes which are made from proteins, so I'm just going to list proteins differently, but obviously enzymes usually are made from them. Proteins and you know, any other chemicals tend to be optically active and will only react with other optical isomers. So that's where we can have a considerable difference. So that's an important one to point out, and it's very important in medicine. For example, in your body you may have a particular amino acid, but it may be either a left or a right, a levo or dextro, a left or right, and that will only react with another optical isomer. It's a bit like shaking hands. You know, if you've got a right hand, it'll only shake hand with someone else's right hand. It will ignore the left hand. It can't shake hands with that. So if that right hand isn't there, of course, it can't shake hands with it, and it can't do it. So it's got to match up. So that's an important thing to bring out. Okay, so with optical isomers you should be able to identify them. That's the 4 different groups. And you should also be able to put asterisks by the asymmetrical carbon, and realizing there can be more than one carbon, although it's unusual in NCA for them to ever ask an example like that. You should be able to draw them in 3D, and that's usually, so obviously you've got to do 2 structures for that to show the fact that you have changed 2 of the groups there. You should be able to talk about the similarities, because they basically are similar with chemical and physical properties, and talk about the differences. Okay, and being careful when asked for a physical test, the physical test is that they rotate plain polarized light in different directions, and be able to explain that. Okay, so you explain it in terms of as light passes through the sample, as plain polarized light passes through the sample, that is, it will be rotated in a clockwise or anti-clockwise direction by a certain amount, and the other enantiomer will be rotated in the opposite direction by that same amount. Okay, that's optical isomers.